Hi guys, welcome to another session on ODEs. Here I have an interesting question. Let u of t, v of t, and alpha of t be non-negative continuous functions on the interval a to b, and v of t less or equals to a of t plus the integral of t, the integral of v of s, u of s from a to t for all t belonging to a b interval. Okay, prove that v of t is less than or equals to a of t plus all this. So we are supposed to use the intercept. So you're supposed to use y of t equals to this. We obtain a differential inequality for y of t and work to the desired inequality. So we work to this. Okay, so first of all, we copy this. Okay, so we have y of t equals the integral of v of s, u of s ds from a, okay, from a to t. And now we differentiate this. So in order to differentiate, we have, when we differentiate this, we have y prime of t equals the differentiation of these. We will cancel out the integral. So we have v of s, u of s, all within the limit of a to t is a. So a to t. So when we simplify this, we get y prime of t equals v of t, u of t minus v of a, u of a. Okay. So with this, we could name this as our equation 1. Then from the proof, from the condition given here, okay, we already have a v of t to be equal to this expression. So we can substitute the v of t equals to this. Okay, so in this here, so let's first make this an inequality. So we can make it an inequality because just to, the hint says obtain a differential inequality. So we make it an inequality. Then the v of t, we substitute the integral expression here in it. So we have y prime of t less than or equals to, so v of t, we put the integral expression which is alpha of t plus the integral expression v of s, u of s from a to t ds. Then we close, then we bring the u of t minus v a u of a. Okay, so from here we then do another substitution for y prime of t. Okay, so but we know that from the equation itself, okay, we've done it here, the equation 1, the previous equation, y prime of t is less than or equals to all this expression. So we put back this expression into this. Okay, so we put this equation 1 into this, so you can make this one equation 2. So you put equation 1 into equation 2. So we'll be having, instead of y prime of t, you'll be having v of t, u of t minus v of a, u of a, less than or equals to bracket open alpha of t plus the integral v of s u of s a to t ds, and we close the bracket, u of t minus v of a u of a. Okay, so when we simplify this, we realize that, okay, sorry, so we have this, so we've simplified, we've substituted the equation 1, okay, which is the y prime. So all this one here on the left hand side stands for the y prime of t, so which is here that we have here, y prime of t. So we put that there, and we maintain this expression that we've already done. Okay, so when we simplify, take the inverse of this to the other side, it becomes 0. So you have this, the inverse of this is plus, plus of this 0, plus of this the same thing 0. So this goes off. So we'll be having v prime of t, so we'll be having, sorry, v of t u of t less than or equals to all this expression now. So alpha of t plus the integral expression then u of t. Okay, so from this we divide both sides by the coefficient of u of t. Okay, by the coefficient of u of t. So we'll be having v of t u of t divided by alpha of t plus the integral v of s u of s ds a t less than or equals to u of t. Okay, so now looking at this, we then integrate. Remember, we can only use the Grunwald inequality to get the desired equation here, the desired inequality here. Okay, so that's what we will be applying. So we integrate both sides. So integrating both sides, we'll be having, so integrating both sides. So this will be the integral of v of, now since we were integrating, okay, and there's already a t here, there's a t here, and we'll be using another t as the integral. Okay, so we change this this independent variable here, the t, we change it to another variable, so we can make it r, because there is already s here, there is, and the r is also here, so we change it to r. Okay, so we'll be using r. So we have v r of u r on a of t plus at v of s u s of ds. So there will be, so we change this one to also s, so this will be alpha, sorry, in t. Okay, dr. So we are changing this to s because there is already the limit, it's a. So if the limit, there is already a here, so we want to differentiate between the two. So that is so we have in less or equals to the integral of from s to t u of r, so dr. Okay, so we having this one to r, so r. Anyway, but if you do not change it, it doesn't matter. It doesn't matter as well. So the next thing is we integrate. So applying the integration rule, we'll be having ln of all the denominators, so a alpha of r plus the integral of all the expression ds, so a to t, then we close, and all this needs to be applied on the limit from s to t, so less or equals to these two, the same thing, but we just maintain this one since we are in need of base expression. So we have s to t u of r dr. So we simplify this, okay, so we'll be getting ln of at plus the integral, okay, vs u of s ds, so t a, then minus the same thing with the next one. So we have the ln okay, so the ln of a. So here we will have ln a alpha s. That's because all the functions are non-negative. So if all the functions are non-negative, the least value we could get for the lower limit is 0. So at everything here tend to 0, then we're having this. So we have this, so less than or equals to the integral. So we just copy the same thing there. Then we simplify this using the logarithm rule. So we have the ln of alpha of t plus the integration of all the functions, the x a to t divided by alpha of s. So less than or equals to the integral expression on the right. So we can further simplify this. So we have all here, this, all the numerator equals the v of t. Okay, it equals v of t from the expression here. So we could substitute this as v of t. So we're having v of t less than or equals to, here we we're taking the antilog to both sides. It's a natural log, so we have e exponent of all this, then this becomes a coefficient, so we have alpha of s, then e exponent u of r dr, so s of t. So we have v of s will be v of t will be less than or equals to alpha of s and all this. Okay. Now since the functions t and s, since they are all the independent variables, just that we just use different independent variable to represent them, so we could say we could suppress it the t to, we could change the t to s. So we have v of s be less than or equals to alpha of s e exponent stu of r dr, and that's easily end our function, our proof. That's easily end our proof. So you could see we've obtained this here, we've obtained that is for this here. Okay, so what is left is just this. So what we do is we just substitute that into the main expression, into the main equation. So we substitute this v of s into this here, into the original function. So we have that. So we have v of t less than or equals to alpha of t plus, so you can write that v of t. So we have v of t less than or equals to alpha of t plus the integral, then v of s. Instead of v of s, this is what we write now. So alpha of s, then e exponent u of r dr. Then we have what? U of s. So the u of s comes. So u of s, then ds over e to t. So that's the limit. So when you compare this, that's all. So this is the same as what we have here. And that's all. Thank you. Do not forget to like, share, and comment. By the way, here is st over st, so that is it. Thank you.